All right, so we're going to finish out chapter 15 in a recorded fashion. So hopefully you did well on your test. So let's get started on the rest of this chapter. So we're going to talk about sea level, which is the area, the elevation where land and water are meeting. And that's over the course of a year. So we can eliminate things like waves, storm surges, and tidal variation. But if we look at that over the course of a year, we we can see what sea level is. And so if we had more glaciers melting, sea level would go up. If we had more ice on the land surface, sea level would drop. Also, if we change the temperature of the water, water that is warm tends to be less dense and it's going to take up more volume, which is going to cause sea level to rise. Now, when we start looking at all water in the ocean, it's going to be rich in salts. And so when we start looking at these salts, most of the salt that we have is sodium chloride, NaCl. Quiz question 2. And so that salt is a product of weathering. When we were talking about rivers, we talked about how rivers carry the dissolved load as one of the 3 types of load. And this material washes down to the ocean. And then fresh water evaporates. And so as a result, we've got a lot of water in the ocean, which means we have a lot of salt in the ocean. If we dried out the ocean and separated the salt from the ocean, we'd have about 500 feet over the entire Earth of this salt. And so again, that's mainly sodium chloride. But almost all of the elements on the Earth's surface are found in the ocean. When we start looking at the sources of these salts, again, that's through weathering of rocks, but we could definitely see at 30 degrees and 60 degrees, 30 degrees north latitude and 30 degrees south latitude, excuse me, we end up with a halocline, a really, really, really salty water. And underneath that is a little bit fresher water. If we start looking at depth, all the water at depth is about the same salinity. If we start looking at water in the northern hemisphere at high latitudes near the North Pole, we've got a lot of land which is going to shut off fresh water. If we shut off fresh water, the salinity is actually going to be significantly less. And if we're around the equator, we're going to have those rainforests dumping a lot of fresh water. And so when we start looking at the salinity of the ocean, it's not uniform on the surface waters, but when we look at depth, we have a pretty homogeneous body of water. Now, whenever we see a bend in a graph, where this is a cline, just like an anticline and a syncline. In this case, this is a halocline, a bend in the salinity graph. Salinity, halo. If we start looking at a variation in temperature, we're going to end up with a thermocline. And so if we start looking at this equatorial regions around the area that's getting more direct sunlight is going to have a warmer surface water temperatures. And so you're going to have a more pronounced thermocline. If we look at the high latitudes, there's virtually no thermocline. Now we're in the mid latitudes, and so we're going to have a little bit of a thermocline, and that's actually going to change throughout the year. During the summer months, our latitudes would actually have one of these thermoclines, but in the winter months, we'd actually break our thermocline. And as it turns out, this breaking of the thermocline, this mixing of this water is going to provide us with some really abundant life because we can actually mix up the nutrients from that depth, and we have sunlight in those, whenever we break those thermoclines, we have a lot of ocean productivity. We'll talk about that in just a second. So density is a function of both temperature and salt content, so haloclines and thermoclines. And as it turns out, this is going to provide some very, very distinct water. So if we have cold, salty water, that's going to be the most dense, and it's going to want to sink down to the bottom of the ocean. And as it does, it's going to actually mix around to create thermohaline circulation belts in the deep waters. And so the one feature as a result of these trade winds, I think I mentioned these in chapter 14 with these global wind belts, these ocean currents in the Atlantic Ocean are moving off the Gulf of Mexico. So we're going to end up with really warm water. In the summer, it can be like 90-degree water, 90-degree Fahrenheit water. And that water is moving up the coast, getting caught in our weather patterns, air moving from the west to the east. And due to the Coriolis force, it's getting pulled up further north. And so that water is going to get cooled off. So this is going to provide cold, dense water. I'm getting the most dense water on the planet. And so that feature is going to cause water to sink and form the deep water thermal haline circulation. When we started having the wind patterns moving over the landscape, over the air, this air movement in the same direction over the same periods of time are going to generate ocean currents. And if we start looking at the all right, so if we start looking at this, I have my pen. Around the equator, we end up with trade winds moving in this direction and this direction as a result of the Coriolis force and those Hadley cells that I mentioned in chapter 14. In this region, the wind is moving from the west to the east in both oceans. And those are called the westerly winds. And near the poles, we end up with easterly winds to the east. And as a result, these ocean currents are going to be moving in a clockwise fashion in the northern hemisphere and a counterclockwise fashion in the southern hemisphere. We call these ocean circulations gyres, and very, very, very dominated by the global winds. And so as those global winds are moving over the waters, there's little eddies that develop in the large bodies of water, and they can accumulate those little garbage patches as indicated here, these eddies. So if we start looking at the global winds, again, you can see that the images are moving from we've got the westerlies where we're located, and this looks like it's a little bit of more of a summer image here. But when we start looking at the Earth, we're going to deal with something called the Coriolis force. And if we start looking at the Earth, it's spinning on its axis. And so that means that different latitudes are going at different speeds. You can see that we're located about 1,000 miles an hour, 900 to 1,000 miles an hour as we're moving around the Earth every single day. And this has a profound effect on something called the Coriolis force. If we start looking at the red line here, this is showing the actual path that a particle would go if we were going to try to go from the North Pole and shoot an arrow straight down into Africa. We would miss Africa by a long shot. And this is because the Earth is spinning out from underneath it. And if we were going to be if we start looking at the blue arrows, this is an arrow going up to from the meeting of those 2 points out to the North Pole, and it's in the opposite direction. So if we're going from the equator to the North Pole, we're going to have to slow down, and so it's going to overshoot, and that's what that overshooting is showing in the blue. If we're going from the pole to the equator, in both cases, it's deflecting to the right. So in the northern hemisphere, this is what I mean by the deflected path is always going to be to the right in the northern hemisphere and the left in the southern hemisphere. If we start looking at the North Pole, it looks like the Earth is moving in a counterclockwise fashion, whereas the Earth, viewed from the South Pole, is moving in a clockwise fashion. So this is why we end up with this apparent movement difference in northern hemisphere to southern hemisphere, known as the Coriolis effect. And so this is caused by the Earth's rotation. Now, as we start looking, winds moving over the Earth's surface, again, a bit of that energy is transferred into the water. And so the deeper you go into the water, the Coriolis effect is going to have a compound effect. The Water motion is a function of the winds. And so the deeper the water, the slower it's going to be moving. And that in turn is going to have more of the Coriolis force over the deeper you go. This is known as the Elkman Transport. It was first described by a oceanographer named Elkman, who was looking at ice sheets and noticed that ice sheets were going slightly different direction than the wind was moving. And this is associated with the friction of the wind movement. And so the deeper you go, you can end up with this Elkman spiral. So you can see this deflecting to the right in the northern hemisphere, to the left in the southern hemisphere. Now, as a result of this, deflection to the right and to the left, this when we have land-water interfaces, if wind is moving in up the coast in North America, it's going to cause downwelling, and if it's moving down the coast, it's going to cause upwelling in the northern. And again, this is looking at it in the northern hemisphere. Everything would be flipped in the southern hemisphere. And so as a result, this upwelling is going to be really important because it's going to break those thermoclines that we just got done talking about. It's going to break the sinocline, and it's going to bring nutrient-rich waters up to an area that has sunlight. As a response, this can produce a lot of plankton, the primary building block of the food web in the oceans. So surface winds that flow away from the shore are going to be moving, causing upwelling. And so we can actually see this upwelling associated with the Elkman Transport, particularly in the Pacific Ocean, because it's so large. And so as a result, this upwelling is bringing up nutrients. And again, we can see right on the off the coast of South America, you end up with a lot of chlorophyll. This is what we're looking at in this image here. And so as a response, I'm going to come back to that. This chlorophyll can produce something called El Nino. So if we want to look at El Nino, here's an actual image of what an El Nino would look like. And that would be when we end up with not as much upwelling, and that's going to create a really strong thermocline. Terrible for fishing, and a good example of that happened in 1997. This has global impacts on global climates, but the next, in 1988, this is a really good example of a La Nina, where you end up with tremendous amounts of this upwelling occurring all along the Pacific Ocean, and this in turn also is going to have its own weather patterns. So here's the actual weather of what we're looking at today, last couple of days ago, on November 27th, we can see that we actually have a really strong La Nina. We're in a La Nina environment. So we're going to end up with really strong currents in this region. Doesn't really affect Missouri too much having it, but different parts of the world are much more affected by La Nina and El Nino than Southeast Missouri. So when we start looking at water currents, I mentioned the thermohaline circulation. This is occurring in the deep waters. As a response to the surface waters, we're bringing up the Gulf Stream, and that's the one that's driving everything. It's bringing warm waters further north, and as the water is evaporating, creating that colder and colder salty water. And so that water is going to sink through the oceans, and you can see it moving through all waters in the ocean, but it's driving those deep waters. And so that water can actually stay in the in this deep water circulation about 1,500 years. I've seen other estimates closer to 5,000 years, but your book mentions 1,500 years as the water molecules moving through that deep water circulation. And again, water is moving up and down, rising and sinking due to density differences as a response to thermohaline circulation, temperature and salty conditions. So in addition to the winds can also create waves. And waves can create ripples, which are small little movements that don't break the surface tension. Again, the hydrogen-oxygen bond between any two water molecules is keeping the water from breaking that tension. But on occasion, what can happen is the water will in fact break, and that's when you're going to end up with whitecaps and water breaking. So when we start looking at waves, moving over the landscape, we, just like in our chapter on earthquakes, we looked at crests and troughs and periods and amplitudes. And so when we start looking at the wave, the top of the wave is a crest, the bottom is a trough. The wavelength is the distance between any two successive crests or troughs. The amplitude is 1/2 the wave height. The period is how long it takes for this wave to cycle through from a crest down to a trough and then back to that crest, or from a trough to a crest and back. So how long it takes to do one orbital period there, one spin. Now, as water is moving, creating this circular pattern, it will actually induce the water underneath it to move in a circular pattern. But we have friction. So that means that the deeper you go, the smaller those circles are going to get. And eventually you get beneath a certain point, about half the wavelength, is going to be the wave base. And that's not going to experience any movement of water. And so when we start looking at the wind, it's a function of a number of different factors: the distance over which the wind is blowing, also known as the fetch, the length of the time the wind is blowing, and the strength of those winds. So when we start looking at the factors that are going to influence the waves, it's all three of the top A, B, and C: the strength of the wind, the fetch, and the length of time that wind blows. And so as these waves are moving in all directions, on occasion, we can end up piling up waves. Two waves can meet, and these are going to be a function of, if you have a crest and a trough coming together, they're going to balance each other out. But on occasion, what can happen is two crests can meet, and then you're going to end up with something called a rogue wave, a really high wave, more than twice as high during any given interval. So one of the other questions that we had was how to break down the ocean. And so some people said using longitude and latitude, and that's looking at those ocean currents. We definitely can do that, but that's not the only way. We can start looking at the ocean in different zones. We have the littoral zone, which is this area from high tide to low tide, otherwise known as sometimes called the intertidal zone. Then we have the region from low tide out into the edge of the continental shelf. Now, we talked about the continental shelf in chapter 2 on plate tectonics, and we said that the shelf is this broad, flat region next to the continent. But then eventually it's going to get really deep really quickly, and that deep water is called the Oceanic Zone. And so if I cover the intertidal zone, the neritic zone, and the Oceanic Zone, that's all the ocean. And as it turns out, most of the fishing is in that neritic zone. But that's one way of breaking down the oceans into how far offshore you're dealing. Then we have some areas, we can talk about the pelagic zone, where organisms are at any depth. And then we have the benthic zone, it's the bottom of the ocean. So we can break down the ocean in terms of depth as being the benthic zone and the pelagic zone. We could actually look at the pelagic zone as the upper portion that has sunlight, known as the photic zone. We can actually have this upper portion, it's called the euphotic zone. Then we have the twilight region and the aphotic, without light zone. And so the benthic organisms would be in the aphotic zone. So when we start looking at life, there's a lot of life in the ocean. That's another way we can break down the ocean, is to what's living in those regions. And so when we start looking at organisms in the ocean, we've got plankton. Now, the word plankton means drifter or wanderer. And so these are organisms that can't swim on their own. They're requiring the use of ocean currents to move them along. And so when we start looking at the plankton, there's two main types. We've got the phytoplankton. These are organisms that are using sunlight to make for their energy source. And the zooplankton are these organisms that eat other phytoplankton and other zooplankton. Then we have the swimmers, which can eat the plankton, or they can eat other swimmers. And then we've got the benthic organisms. These are organisms that are on the ocean surface. So an organism that lives on or above the ocean surface is referred to as one of those benthic organisms. Now, when we start looking at these planktons, um, as it turns out, here's an example of one of these. These are going to, in many cases, continue to grow as long as there's enough nutrients and sunlight for them to grow. And they can reproduce really, really quickly. The lower image is some zooplankton that are eating those phytoplankton. So if they bump into the phytoplankton, and so they're going to be limited by the number of phytoplankton. So here's some examples of some of the swimmers, the nectins. These are things like sharks and whales and fish, and then the benthic organisms. Now, trying to figure out how these organisms all interact is known as a food chain and more broadly a food web. So we can see that the phytoplanktons would be the primary producer. They would be the first organism in the trophic level. They're also known as autotrophs. They can produce their own energy, whereas opposed to the zooplankton, which are heterotrophs, which have to eat autotrophs for their energy source. And so we can try to track down what the impact of these food webs are. There's a number of good videos that look at what happens when we disturb these food webs and the impact on these organisms. There was a new article last month of we'd expected if we got rid of a lot of whales due to whaling, we'd expect the whale food to their numbers to really go up. And as it turns out, it wasn't the case. The reason why is whale poop apparently is really rich in nutrients, particularly iron. And the iron in the oceans went down when we didn't have as much whale poop. And so as it turns out, that nutrient limited the amount of algae in the oceans. And so we can see that these food webs are much more complex than we gave them credit for. So when we start looking at nutrients in the ocean, it's usually phosphorus, nitrogen, and iron. And so when we start looking at these organisms, we can see that in some cases, we can produce these regions known as dead zones. Well, what can happen is these algae can use up all of these nutrients. So if we have an abundance of phosphorus and nitrogen or iron, and unfortunately in the Gulf of Mexico, due to soil erosion and over fertilization of some of our agricultural land, some of those nutrients are making their way into the ocean. Now, some might think that's a really good thing, but actually it's a really bad thing, because what's going to happen is the phytoplankton are going to use up all of the nutrients, and then the algae that are going to be in really abundance are going to block out the sun. And so this can create the algal blooms are going to remove the oxygen, mainly the zooplankton are also going to reproduce really quickly and use up all of the oxygen. And as a result, these are going to create these big, broad regions of organisms, free environments known as dead zones. And so if we wanted to see some of these dead zones, unfortunately, the Gulf of Mexico would be an example of those. So if you have any questions, I wanted to just kind of quickly give a little video so we didn't have to wait for others to finish the test. But we'll get started on chapter 16 on Tuesday. Talk to you later.